we're going to tackle some problems called trigonometric integrals. The game here is to mix up U substitution and trigonometric identities to simplify an integral. We have to agree on the fact that we can always exchange even powers of sines for cosines or vice versa because of everybody's favorite trig identity, sine squared plus cosine squared equals 1. So if we have a sine to the fourth, a sine squared, a sine to the eighth, this identity can be used to change all of those sines into cosines, and vice versa. And so what we have to do when we're faced with an integral like this, which is a mess of trigonometric functions, is how can we combine the process of substitution and this process of exchange of even numbers of either sines or cosines to make everything shake out. Here's how that goes. Here we're looking at the antiderivative of cosine squared times sine cubed. If we're going to tackle this with U substitution, our two primary best candidates of what kinds of substitutions to pick are either going to be U equals sine of x, in which case du needs to be cosine x dx, or U equals cosine of x, along with which we'd have du equals negative sine of x dx. So if we put this substitution in play up here, notice that there's three sine functions, sine cubed. So if we put this substitution in play, this would be a u cubed, right? And then for the du part, well, one of the two cosines available would become part of du. And then we have a single cosine of x still floating around. The substitution isn't going to help, and we can't turn it into sines because there's only one of them now, not two. So this would be a bad substitution. A better substitution would be to let u be cosine of x, and so this term becomes u squared. With that choice, we need one of the sines for a du, so of the three sines available, one of them becomes part of du, and then we have sines squared left over, which we can then turn into cosines and then keep using our direct substitution. Okay, maybe it's easier just to show this. First of all, knowing that I'm anticipating the use of one of these three sine functions for du, I'm actually going to physically peel one of them off and write sine cubed as sine squared times sine. And then I'm going to think about this substitution right here, u equals cosine x. This term right here is going to be a u squared. This part right here, based on my substitution, is going to be negative du, right? If u is cosine of x, du wants to be negative sine of x dx. Well, this is a positive sine of x dx. No biggie. That's just a negative du. And what do we have here? Well, we have sine squared. Our substitution is for u equals cosine squared. That's fine. Sine squared is 1 minus cosine squared x. And with our substitution, that's 1 minus u squared. So I've slopped everything all over the place here, and I already have another problem ready to go, so I can't use up too much more room. But what I've done is with this substitution, I can turn my integral into the antiderivative of u squared times 1 minus u squared times negative du. There's my du. I'll put the minus sign out front here. Now, I'm not going to carry this farther because you can multiply this out. This would be u squared minus u to the fourth. Hit it with the power rule a couple of times, get it done, and then reverse your substitution. The tricky part here is making the choice of which substitution are we going to do. Now, maybe this was a little bit intimidating because there's 5 trig functions altogether, cosine squared and sine cubed. So what happens? Oh my goodness, cosine to the 8th times sine to the 5th? Wow. Well, nothing really different happens. In fact, the same substitution is going to do the trick. We either are going to set u be sine of x or cosine of x, and we have to borrow one of cosine or sine to make the du work out as well. The even-numbered powers we can always exchange with our trig identity here. So I'm going to do the same thing I did above. I'm going to write this as cosine to the 8th times sine to the 4th times sine of x dx. Whoops, I forgot an x. Good grief. And I'm going to use this substitution all over again. The cosine to the 8th just becomes u to the 8th. That's the direct substitution. Sine to the 4th is sine squared squared, right? Sine to the 4th is sine squared squared. Well, sine squared is 1 minus cosine squared. And with our substitution, that's just 1 minus u squared squared. And then the sine of x dx, well, there's our negative du one more time. And so these trigonometric substitutions allow us to take something that's pretty nasty and turn it into a power rule problem. Now, this is a power rule problem is a lot worse than this one was because there's a lot of multiplying out to do here, right? I'll continue a little bit. This would be u to the 8th times 1 minus 2u squared plus u to the 4th du. So then you got to multiply through that u to the 8th and then do the power rule on 3 separate terms. But again, that's Calc 1 stuff. So you should be able to take over from there. Now, what if you don't have sines and cosines? What if you have, oh man, tangents and secants? That's terrible. Well, first of all, who remembers the identity for tangents and secants that looks like this one? Nobody remembers that off the top of their head. Or if you do, you have to puzzle over it for a minute. And I'm going to argue that you don't actually have to remember it. I'm going to put this in the way just a little bit. As long as you remember this one, you're good to go. Because if I want to introduce tangents and secants, just imagine taking this whole thing and dividing the whole thing everywhere by cosine squared x on both sides of the equation. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. And there you go. There's your identity involving tangents and secants. The same rules are going to apply. The same strategy is going to apply. We're going to try to decide which of these two substitutions is the best one. Either I'm going to start with u equals tangent of x, which means I need a secant squared left over for du, or I need a substitution u equals secant of x, in which case I need du to look for a secant x times tangent of x dx. And so it's all a question of what can I wipe away with my substitution, and what exchanges can I make of even powers of tangents and secants. So let's just kind of think it through. Suppose I used u equals secant of x. I would love to put secants all over the place then to make that substitution work. And I can convert even powers of tangents into secants using my identity. But if I try u equals secant of x, then one of these secants right here is, well, actually all 4 of them. If I use u equals secant x, then I need to reserve a secant and another tangent for part of my du, right? So to apply this substitution to this antiderivative, a secant and a tangent have to stay reserved for du. So the 3 remaining secants would just be u cubed. But if I've reserved one of these tangents to go along with the du, that means I have 5 of them left. And I can't convert 5 tangents over to secants. I could convert 4 or 6, but not 5. So that substitution isn't going to work. So maybe this one's better. To let u be tangent of x, that means I need 2 of the secants in reserve for du. Okay, so let's try that. Let's see if I can put 2 of the secant functions in reserve for du. Is this going to work out? Well, this is all accounted for in the substitution. This part of it's just going to be u to the sixth, because remember, I'm using this substitution now. U is tangent of x. And what am I going to do with my leftover secant squared? Well, remember, I can turn even powers of secants into tangents, and the identity is this. Secant squared is tan squared plus 1. With my substitution, that's going to be u squared plus 1. And so this is u squared plus 1. And so I start with this antiderivative, I use this substitution with a trigonometric identity in play, and I've converted the whole thing into a power rule problem. And now I need to solve that antiderivative. I'd multiply it out, I'd use the power rule a couple of times, and then I would reverse my substitution back to the original variable.